Hi everyone, now we are going to see about the density of energy states. So first we should recall what is Fermi function, what is Fermi-Dirac distribution, what is electrical conductivity, how electrons are distributed, and probability of occupancy. So these are all already we discussed. So what are the topics now we are going to discuss? Introduction to density of energy state, then importance of density of energy state, uses of density of energy states. So why we need to understand this density of energy states? So electron distribution, we should know about electron distribution and number of available energy states. How many number of available states are there and how the electrons are distributed in that state. Then the material semiconducting property, and that means electrons and the whole concentration that we can find. Next is electrical conductivity. So it determines the material conductivity. Next is a Fermi level. Fermi level is used to electron occupation probability. Next, electronic devices, basics for diodes, transistors, solar cells, and light emitting diodes, etc. So, energy analysis, understanding how electrical electron occupancy is different in different energy level that we can find. What is the density of energy states? That is simply called DOS. So density of energy state is the number of available electron energy states per unit energy range at a particular energy level. So simple definition for this is tells how many energy states are available for electron at a given energy level. That's all. So for a 3D free electron system, that is a G of E is equal to 1 by 2 pi square into 2m by h crosses. H crosses h by 2 pi. H crosses square 3 by 2 into root of E. Key ideas: density of states plus Fermi-Dirac distribution. So number of electrons at a energy E is equal to G of E into F of E. F of E, what is F of E? F of function of energy states. So density of energy states. So definition for this is density of energy state is the number of available electron energy state per unit energy range at a particular energy. So its mathematical expression is symbol is G of E, and G of E for a 3D free electron system, G of E is equal to 1 by 2 pi square into 2m by h cross squared whole power 3 by 2 into root of E. And here number of electrons at a energy level E is equal to G of E into F of E. So what is G of E? G of E is density of states. So we can find the number of electrons at energy E is equal to density of, it's a product of density of states into Fermi-Dirac distribution. What are the applications of density of states? Semiconductors. Semiconductors, it determines the number of available energy states for free electrons and holes. Then EG, here EG is energy gap. So Fermi level analysis, it is used to help study electron occupancy at a different energy levels. In this energy levels are in this energy state, how many electrons are occupied, how many electrons are can occupy, what are the availability. So that and all we can check. We can, next is electrical conductivity, helps understand the availability of electrons for conduction. If free electrons are available or not, that we can find. Next, electronic devices, useful in analyzing diode, transistor, and solar cells. Then optoelectronic devices helps explain light absorption and emission. Next is material properties, used to study the electronic properties of metals, semiconductors, and nanomaterials. So summary of this density of states, it is a density of states is defined as the number of available energy electron energy state per unit energy range at a particular energy. Next, the key formula for density of state is G of E. G of E is the density of states. G of E is equal to 1 by 2 pi square into 2 m by h cross square whole power 3 by 2 into root E. And here G of E gives the number of available states and it increases with the energy. Then combines the Fermi-Dirac distribution to give electron occupancy. Their applications are semiconductors, determine the available state for electrons and holes, then electrical conductivity, explain electron availability, electronic devices analysis of diodes, transistors, solar cells, then optoelectronic devices explains light absorption and emissions. Curiosity challenges here. So try to answer for this question. The questions are very interesting one. Some of the references given here. Yes, thank you.